So students, now we are at the last module, that is module number 3 of this particular chapter, and in this particular module we are going to talk about acid-base catalysis, base versus nucleophile, and some recap questions to revise whatever we have done in this particular chapter. So what is acid-base catalysis? Now, whenever any acid or base takes part in the chemical reaction and enhances the rate of reaction, then we will call that as an acid-base catalysis. Some of the reactions are acid catalyzed, while some of the reactions are base catalyzed. Some typical examples of acid-base catalysis reactions are esterification, aldol condensation reactions. Esterification is possible with both acid catalysis as well as base catalysis, and as per whether it is acid or base catalyzed, the mechanism changes, as well as aldol condensation is possible as both acid catalyzed and base catalyzed. Now, in these reactions, the conjugate acid of compounds like carbonyl group becomes a good electrophile than neutral carbonyl group itself. Depending on chemical species that act as an acid or base, catalytic mechanism can be classified on the basis of that as a specific or sometimes general. So first example we see, that is ester hydrolysis. Ester is RCOO R-. Now, if it undergoes hydrolysis, it will produce acid and alcohol as products. So, it is possible that a base catalysis as well as acid catalysis of ester hydrolysis may occur. All these are reversible reactions. The first one is a base catalyzed, OH minus is a base. Now, this OH minus undergoes nucleophilic addition to this carbonyl group to produce this particular species. Once this is formed, then it breaks down to give you acid and alkoxide ion. Now we know that acid is a proton donor and alkoxide is highly unstable. Because of that, immediately in aqueous medium, it gets converted into alcohol and acid generally remains in ionic form. Again, here you can see OH minus is generated. That means your acid is regenerated back and the medium will be alkaline or basic. So this is how ester hydrolysis base catalyzed reaction can be represented. Similarly, this ester hydrolysis can take place by acid catalysis. Now acid either H plus or H3O plus. Now this is proton rich. So what happens? It gives proton to the carbonyl group and protonates the oxygen atom of carbonyl to form this oxonium ion. Once this undergoes protonation, it breaks down to give you a carbocation. The carbocation form undergoes hydrolysis via this intermediate forms an acid and alcohol as a product. So here again, after ester hydrolysis, you're getting acid and alcohol as a product. Only difference, their mechanisms are totally different. Similarly, as I told you, that even aldol condensation can take place by both mechanism, that is base catalyzed and acid catalyzed. If it is base catalyzed, then you'll find that alpha hydrogen atoms of aldehyde or ketone, which are acidic in nature, they are abstracted, a carbanion is formed, and that carbanion then further undergo condensation to give you alpha beta unsaturated aldehyde or ketone as a product. Similarly, in acid catalyzed reaction, here the protonation takes place and reaction goes with different mechanism to give you again alpha beta unsaturated aldehyde or ketone. So aldol condensation or ester hydrolysis, and there are many other examples where acid-base catalysis is observed. So let us talk about now the basicity and nucleophilicity of any ion or a molecule. See, many times we get confused with that whether given species will be a basic or whether it acts as a nucleophile. If it is base, then it brings about elimination reaction, and if it is nucleophile, then it will bring about the substitution reaction. We can classify them broadly as strong base and weak base. If I have a strong base, then generally it goes into elimination, that is E2 mechanism. The details will be seen in elimination reaction chapter, but for the time being, just understand that if you have a strong base, then it will bring about elimination reaction. Halides and azides, anions are nucleophilic but not basic. Only strong nucleophiles that are not as strong bases, and they are the nucleophiles and not the strong bases. So here are the few examples where these will generate strong bases like NaOH, KOH. They will form OH minus ions, OR minus ion, which becomes a strong base. Soda amide, NaNH2, ionizes to give NH2 minus, again a strong base. Weak bases, they are generally neutral molecules, and they generally brings about the elimination even type of reactions, or they bring about the SN1 type of reaction. You can see, for example, water, alcohol, H2S, RSH, these are weak bases. Why? Because oxygen here can donate electron pair, and therefore they are basic in nature. Similarly, our sulfur, these are electron rich species, can donate electrons and become weakly basic in nature. So we have understood that just like bases, we can classify nucleophile as strong nucleophile and weak nucleophile. So nucleophile and will bring about nucleophilic substitution reactions, maybe SN1 or SN2 reaction. A strong nucleophile generally goes to SN2 mechanism, whereas a weak nucleophile goes via SN1 mechanism. So if I compare this now, let's say I've got water and OH minus. A negatively charged species will be a strong base as compared to neutral. Therefore, OH minus is a strong base as compared to water. Methoxide ion and methanol. Again, methoxide has a negative charge, becomes a strong base as compared to methanol. NH2 minus and ammonia. It's a neutral molecule. This is negatively charged, becomes a strong base or a good nucleophile. Similarly, in these two species, here NH minus and this is NH2, this is negatively charged, therefore becomes a strong base or a better nucleophile. If you have a strong base, E2 elimination will take place. If you have a good nucleophile, then SN2 type of reactions are possible with such kind of species. So various comparative aspects of nucleophile and base are given here. Kindly go through, and we have already discussed about it. Just try to read and revise these things. Let us solve some problem based on this. Now let us take these. These are conjugate acids of bases. This is triethylamine and this is diethylamine. These are the conjugate acids of these bases. And what you'll find that a diethylamine conjugate acid is more acidic as compared to triethylamine. Or in the words, what we'll say that diethylamine is a stronger base as compared to triethylamine. So large difference in pK is observed for the conjugate acids, and this is because the stabilization of these conjugate acids. If I take water and H2S, now both have two hydrogen atoms, but they're attached to oxygen or sulfur. Now we know that oxygen is highly electronegative and sulfur is less electronegative. So the pK value of water is 14 and H2S is 7. So H2S is a strong acid as compared to water. Take the example here, OH minus, H2O and H3O plus. The acidity goes on increasing This rather OH minus is basic, water is neutral, and H2 plus is acidic in nature. NH2 minus, ammonia, and ammonium. NH2 minus is a strong base. Ammonia is a nucleophile, whereas ammonium is acidic in nature. So their pK values, you can always compare them. If across a period, if I move carbon to nitrogen, nitrogen to oxygen, oxygen to fluorine, I know size goes on decreasing, as well as the electronegativity goes on increasing. If the electronegativity increases, the pK value will decrease. HF will be stronger acid as compared to water, water will be stronger acid as compared to ammonia, ammonia will be more acidic as compared to your methane molecule. So these are the example. Let's say if I compare your methanol with phenol, phenol is more acidic as compared to ethanol. Why? Now see the pKa values. This is 15, this is 10. Lesser the value of pKa, stronger is the acid. So phenol will be more acidic, whereas methanol are neutral. Methanol is neutral. Alcohols are neutral, whereas phenols are acidic in nature. Why it is so? So what you'll find, after ionization, a phenoxide ion is formed. After giving H plus ion, the phenoxide ion form is stabilized because of resonance. This ring is used for the stabilization of this ion, and because this anion formed is highly stable, makes phenols acidic in nature. In case of methanol, this stabilization is not possible. The methoxide ion or any alkoxide ion formed from alcohol, you know that there is negative charge on oxygen and R group is electron donating, makes it highly unstable, and therefore alcohols are neutral in nature. If I take methanol and acetic acid, now here what happens, the anion formed, that is acetate anion or any carboxylate anion, if I take for always carboxylate acids will be strongly acidic as compared to alcohols. You can see the pK value, there is a large difference. Acetic acid pK value is 4, whereas methanol is 15. Again, what is the deciding factor? The anion form is stabilized because of this resonance. Carbonyl gives a resonance stabilization to this ion, as well as carbon is electron withdrawing, so makes this anion form highly stable. And stable, if the stability of anion increases, acidic strength will increase. No such stabilization is observed in case of methanol, therefore it is neutral in nature. Then, if I take these examples, what you'll find now, this is your acetic acid, then iodoacetic acid, then bromoacetic acid, chloroacetic acid, and fluoroacetic acid. The pK values, if I compare, the fluoroacetic acid is the strongest, whereas acetic acid is the weakest among this. What is happening here? So hydrogen is replaced by iodine, iodine is replaced by Br, Br is replaced by Cl, and Cl is replaced by fluorine. And we know these are the halides in a group. As I go from fluorine to chlorine, chlorine to bromine, or bromine to iodine, the size goes on increasing, electronegativity goes on decreasing. Fluorine is the most electronegative, it shows minus I effect, stabilizes the anion formed after ionization. Because the stability of anion increases with minus I effect, these acids become stronger acid, whereas in case of acetic acid, this stabilization is very poor, as hydrogen is neither electron donating nor electron withdrawing. Therefore, the acid strength is observed in this manner. Another example we'll see now. Here, this is 1, 2, 3, 4 carbon containing acid. So it is a butyric acid. Now here's a bromobutyric acid. Here bromine is attached to alpha, beta and gamma carbon. Here it is attached to alpha and beta, and this is attached to alpha carbon. So alpha bromo, beta bromo and gamma bromo. Now what is the tendency of Br? Br is electron withdrawing. If I replace hydrogen by Br, the electron withdrawing capacity of Br is much greater than hydrogen. So you can see the acidic strength goes on increasing, the pK value goes on decreasing. Lesser the value of pKa, stronger is the acid. So alpha bromo acetic acid will be stronger than beta, beta will be stronger than gamma. Why? Because in anion stabilization, inductive effect as the distance increases will go on decreasing. So here the distance is least, only one carbon is there. Here there are two carbon atoms. Whereas here there are three carbon atoms in between. So inductive effect will be poor in this molecule as compared to this, and it will be less as compared to the alpha bromo. Therefore, alpha bromo acetic acid is a strong acid, whereas gamma bromo, your butyric acid, will be a weak acid. If I take, let's say, ethane, if I take benzene and acetylene, what is the difference? Here hydrogen is attached to sp3 carbon, here hydrogen is attached to sp2 carbon, and here hydrogen is attached to sp carbon. If the hybridization changes, percentage of S character is different. In case of sp, it is 50%, sp2 it is 33%, and sp3 it is 25%. That affects the acidic strength. More the value percentage of S character, more will be the electron withdrawal capacity, and higher will be the acidic strength. So you can see pK value 50, 42, there is not much difference in the pK value of these two compounds. But if you compare with acetylene, acetylene is quite strongly acidic as compared to benzene or ethane, because here the hydrogen is attached to sp carbon atom. So when I go from sp3 to sp2 or sp2 to sp, the acidic strength goes on increasing as the percentage of S character increases. If I take this molecule, now here NH2 is attached to again sp3 carbon, NH is attached to sp2 carbon, NH is attached to sp carbon, or hydrogen is attached to an oxygen with positive charge, hydrogen attached to bare oxygen. The strength will be different for all these acids. If I take acetic acid, ido, bromo, just now we have discussed, electronegativity goes on increasing, acid strength decreases. There is one more example, the position of Cl is alpha, beta, or gamma, and as the distance goes on increasing, the stabilization will decrease. Alpha position stabilizes maximum, and therefore the pK value is the least for alpha chloro, this acid, alpha chloroacid, and therefore it is strongly acidic in nature. Remaining almost pK values are same for other acids. You take this example, now here what will happen, acetic acid, monochloro, dichloro, and trichloroacetic acid. When I replace hydrogen by Cl atoms, you'll find that their K values goes on increasing and pK value goes on decreasing. So trichloroacetic acid is the strongest acid. The pK value is smallest 0.64, very strong as compared to acetic acid, which is weakest acid among these three. So these are the various factors we have already discussed about, which will decide the strength of acids as well as bases. Here again you can see iodine, Cl, here you have methyl, and you have chloro at alpha and beta position. The K value goes on increasing, or the pK will decrease, strength of acid will increase. We have discussed NH is attached to two phenyl ring, NH2 is attached to only one ring, whereas NH2 is attached to sp3 carbon. In case of bases, if resonance is there, that makes it, the lone pair is in conjugation, not easily available, makes it least basic. So diphenylamine is least basic among these. Aniline is more basic as compared to this, whereas your cyclohexylamine will be the strong or most basic in nature. Their pK value will be higher if it is base, and pK value is less if it is acid. So this is how we can discuss about the various factors which will be responsible for the strengths of acids and bases. Here are some examples where we have shown how they undergo ionization and what are their values of pK. You can always find out from K the pK values and practice the conversion of pK into K or K into pK. So these are the various types of acids. Some of them are monoprotic, diprotic, triprotic acid, why something is strong, why something is weak. All these comparative aspects we'll be talking about based on various factors we have discussed in module 1, module 2, and as well as in this module. So here are some practice questions for you based on this model. Try to answer these questions, and we'll discuss this later on. So try to solve these problems. Thank you so much.